Welcome back to the part D of lecture 12. In this video, we are going to do some hands-on. So, let me start my R. In this, so we will still work with the iris dataset. So here I'm going to first create a null plot. So I will just first see how the how the data looks like. So I'm going to see on the x-axis I'm going to put sepal length, on the y-axis I'm going to put sepal width. So I'm going to name the species. There are three kind of species are there, and their species color I'm going to assign blue, red and brown, and in the species color I'm also giving the name. Setosa got blue, versicolor got red and virginica got brown. And then I am saying that legend, put the legend on the top right. So the Setosa blue, versicolor red, virginica got brown. You can try some other color, no problem. Now I'm calling MVT norm package. If you don't have the package, please install by here. You can go to the package, then install and write this thing MVT norm. Make sure your install dependency is corrected and then install. That will work. I am cancelling it because I already have it here. Setting a SID here. This function, one line function, will help us to draw an ellipse or the contours of the Gaussian distribution. So x0 is the point for, it's sort of 6.2 and 4 is the point we are going to use as a test point, and then I'm going to create a f0 with the name species. So f0 is going to be my likelihood or function. So I is in species. So there are three species. For each species I'm going to work with. From the iris dataset, what I'm going to do, whenever iris species equal to the species name, then you just take the sepal length and sepal width, that will be the x. Okay, and then you compute the covariance matrix of these two columns and the mean of these two columns. Now given this mean and this covariance matrix, you simulate 1000 points and compute the center of the point and the covariance of those points. Okay, and then you calculate the sigma inverse. So that gives you then you use this mu and sigma to calculate call that multivariate normal density. Put it in the DMV norm is the density of the multivariate normal, and plug it in. This is the likelihood value of the multivariate density for x0 point. X0 is the point at which we want to estimate. So what is the likelihood for that point? Then for n equal to 100, we creating x-axis, y-axis, and we are saying that okay, please draw in this line, we are three lines, we are drawing the contour for that particular species. So let me just run this loop. So here is the viewer plots. So here is the plots. Okay. So let me just run the points. So these are the 3 points and 3 and then here is the test point. Here is the test point. You see, this is the test point. Now I am going to give equal prior probability. I am not saying, so prior probability for this point belong to setosa, versicolor or virginica is equal. I am not giving any special additional preference to any point. So the name prior of the, now I just add the names also, and then I'm just computing the base probability. Okay, and rounding off the base probability up to the 3 decimal places. So here, so that means base probability is 0.861. This point belongs to setosa with 80% probability, to versicolor with 2.9% or about 3% probability, and 11% probability that it belongs to virginica. So with a high probability we will say that most likely this point belongs to setosa. Now we are going to do this is for one test point. So I try to demonstrate how linear discriminant analysis in theory using one test point, but most of the time you will see that your data will have many test points and you have to run it like a typical ML setup, machine learning setup. So I am going to take the iris dataset with here is the iris dataset with all the 150 values with 50 in each probability, and then I'm going to first split the data into train and test. Okay, split the data into train and test. Okay, so I just played the data in the data table. If you just say, so basically in train data there were 33 setosa, 32 virginica and 35 versicolor, so they're almost same. So out of 150 samples I have taken 100 random samples from the main data, and those samples belongs to train data sets. 100 samples belongs to, and 50 samples belong to the test data set. Here in this I'm going to fit LDA, linear discriminant analysis, and I'm saying that okay, fit all the models. So maybe I will just say head Irish. So maybe first I will fit with the length plus sepal width, maybe with petal length. Okay, with 2 feature, essentially with 2 feature. This is my first model, and if we just run this, then we can do the same with the predictive class. And then this is the result one. And this is the confusion matrix. Essentially, actually this is more like a confusion matrix. So I would rather, instead of result, I would say it's a confusion matrix. And let me just show you how the confusion matrix looks like. Okay, there are 2 cases where virginica, which were virginica, that was classified as versicolor. Okay, So this is the linear discriminant analysis with 2 features. Now let me run the entire thing with maybe model 2, and what we can do and train Irish. So let me now just put the sepal width and petal width as well. So all the features, all 4 features, let me put all the 4 features, and let me do the prediction. And out of the sample prediction, remember that here is my test data set to do the prediction. Okay, and then this is the confusion matrix. So let us run this confusion matrix. Now it is being corrected. So when we put the more feature, naturally the classification becomes better. So, and it is in the out of the sample classification it got better. So this shows that if you have more feature, more typically it helps you, but at the same time you have to be careful about the overfitting, that if you put too many features, too many engineered features, you might end up in a wrong place with a lot of overfitting. That means in your test accuracy and out of the sample accuracy and in sample accuracy will be very different. At the same time, remember that you have to be, this particular dataset, IRIS dataset, is actually a very toy dataset. Going forward, we will try with more real life, new days dataset, new age dataset, where it will be much difficult to classify the target variable. With this, thank you very much. Wish you a happy weekend. See you in the next week with new lecture, new topic. Thank you very much.